All right, welcome back. Cohort 4. This is our second discussion of chapter 10. Next week will be our final week overall. So we'll talk about future textbook groups, give a little time, or people can fill out the forms now for feedback. They can add feedback. There's a lot of other pieces that we can talk about, but this will be the last recorded conversation. So nice times. Let's go to 10. And does anybody want to begin with any question, or we'll look at what's already been written?
So Daniel, I have two questions, kind of general. Since I'm new to this process, one of the questions that I wish I had asked you sooner was, as we participate and contribute in this process, are there certain things that you would like to see? That the authors would like to see. So what I'm wondering about, like in terms of feedback that we can add through time is, are they concerned about it, what audiences they're attempting to reach? Are they concerned about what principles, what concepts might go over people's heads and make them turn away completely from active inference prematurely? So that's one question that's general. The second question I have is, and I added a row in the coda. I was thinking that if one of the objectives of this book is to have people who don't have the physics background walk away thinking, I would like to apply this to the work that I'm doing. And of course, this is very selfish because I'm basically describing myself. So if we don't want to lose people, could there be a document somewhere, and if it exists, let me know, where it basically has a list of, okay, in order to fully understand, and I'm just going to say the free energy principle as an example. In order to fully understand the free energy principle, here is a pathway of knowledge that you need to complete. And it goes in a sequence from, concept A to concept N. And then you have the concept, the equations, if the concept comes with equations, and then just very succinctly described, you need to know this and you need to know this, and then links to videos and resources online, so that basically a person can follow a self-directed learning pathway. And one of the things I've done over the past week is I decided I want to take a deep dive into the free energy principle. Where did it come from? Who came up with it? How did they use it? Do they use it in physics, in engineering, etc.? And I have found that it's really helpful. So that was my main comment for today.
Thanks. Okay, I'll give short responses to each, and then anyone else can add. So what with the authors like Parr and Pezzulo and Friston, I mean, they're happy that we're enlivening and working with the textbook. We started doing it obviously like the first day that we could, and we've given them feedback on little typos and minor things, but also people have engaged with them on more substantial topics. And they as authors and as the publishing company, they're at least open to our proposals. There's no questions in the textbook. And that one textbook isn't the be all end all. So it's definitely, I think, great to see how we can serve the authors and also the broader niche. And in terms of like all backgrounds in the generalized learning curriculum, like this textbook group is low effort, all things considered. We don't have to prepare the materials, and especially now having gone through it multiple times, we just show up and enjoy. But the broader project of making knowledge spaces so that people can have self-guided and have that be like across different languages and technical backgrounds, I mean, that's the educational project that the Institute is working on. So for that, we just need people who are seriously committed to actually engage in that. At a slightly smaller scale, Ollie, I believe, in the resources page, this list of papers goes from less formal to more formal, but this is an infinite regress. You're going to find that you keep on pulling back to fundamental concepts, which may be good. But yes, the textbook group is not the total educational paradigm. It's just one offering, and we eagerly look for people who want to stand up the textbook group and see what it can be. All the low-hanging fruit, like filling in the natural language descriptions of the equations and curating the discourse and adding more notes and all these things. And then also the reach goals for the textbook group, like developing the software repositories that have the examples and all these other things. And then even the broader educational goals that go outside of the textbook group.
Thank you. Appreciate that.
Anyone else have a thought on that? Yeah, Ollie.
Yeah, so I believe being a relatively new discipline and even a new, research niche, I don't think active inference has reached its full form yet in terms of being totally structured around a definite roadmap and so on. So it's a bit like neuroscience at large. So we know that unlike many other disciplines, such as, I don't know, physics or mathematics, which have a relatively more structure to the knowledge base they have, in such disciplines as neuroscience or active inference or many other cognitive science and psychological sciences as well, we don't have this definite roadmaps yet. So one way to approach active inference is to somehow determine the target topic we try to study using active inference framework, and then try to find kind of rhizomatic or multi-branch ways to approach or at least converge onto that topic. So if we expect the learning path of active inference to be a totally linear and coherent pathway, getting us from point A to point B and beyond, I believe we might be disappointed at finding out that there isn't any such roadmap yet. Obviously, in coming years, there might be more structure to the learning path of active inference, but as it's typical for many other new disciplines and research areas, we're still exploring the forests, and we don't have the cartography of the whole area yet at our disposal.
Thank you.
Yeah, that makes perfect sense. I think so. I understand that because fully. So I would say that in my previous conceptual work, primarily in evolutionary biology, anthropology, and the extended evolutionary synthesis, I think people would say, for example, if I want to apply the concepts of niche construction to my field, is there a linear path? No, there isn't. If I want to include everything that's underneath the extended evolutionary synthesis, no, there's no, it's completely, it's quite tough actually to connect all the big areas that people have worked on. But I think there might be room somewhere in the Active Inference Institute to start thinking about at least like the very basic fundamental concepts. So I think that if somebody sat me down and said, I want you to do this for the extended evolutionary synthesis, I think I could sit down and say, if you don't know these things, you're going to be completely lost in this literature. So there may be some foundational aspects to in this framework that could be made accessible. So to me, it's all about accessibility because, so why am I so concerned with this? It's because I've been looking for 20 years for a conceptual framework that I feel actually addresses aspects and phenomena that I have been looking at for this long in what I call regenerative population health with a focus on humans. And the active inference framework is the first framework I have found that actually I can tell has the potential for allowing me to talk about things I couldn't even begin to talk about before, that things that I can actually give names to. And so in my case, since I ultimately have a very applied aspect to this, which is I work on population health projects in education and hopefully soon in communities, there's a certain urgency that I feel that I can't go, for example, into an audience of public health scientists without being able to say something about why it's important to understand the free energy principle. And that's what I'm struggling with.
Yeah. We're like making 1,000 small tracers with people's questions here. No questions, no tracers. 1,000 questions, 1,000 tracers. We can use curation and attention as well as language models to synthesize what we already have written into many of the bases. Now, there's actually two components of what you ask, which is the necessary and sufficient information and the sequencing. Sequencing in linearization is a separate question than what are the fundamentals. The fundamentals are what are covered in this textbook, Sanjeev's textbook, the literature. Those are the topics that we return to again and again. Now, they might be challenging, which then begets the question of learner-specific sequencing and context-specific sequencing, having the situational awareness to know what you need to go into or not when you're conveying active inference for a certain audience. But yes, we, as part of a broader educational project outside of just the textbook group, can use the ontology and other techniques to develop knowledge systems that let us address these questions. We're very, very recently in the game and with very, very few people months dedicated to the broader educational project. But if it's something that people want to do, there's always a niche for people who want to contribute to active inference education by doing something that's much like the textbook group, like for cohort 6 or something, or by diving back into the work that people have done over the years on the broader question, like the fundamentals here that Brock started, I guess a year ago, or the other educational kind of first takes. It's just a big journey. But again, with our knowledge engineering project and our literature compilations and all these other things, it's the challenge that we'll address.
Yes, there are so many, I'm finding all kinds of resources as you're talking. On the website. Thank you. Appreciate it.
Cool. Any thoughts on 10 or any other questions? Sean, you asked about the computational complexity. As far as
yes, I did. Yeah.
As far as I know, the best, Ali, please correct if we have different information, but I believe that the best information was the computational complexity right here in the branching time active inference paper and model stream. The computational model stream 6.1 branching time active inference paper. Here's 21 minutes in. And actually the computational complexity of active inference is like, it's almost what you'd expect.
Is it NP hard problem or it's just
I'm not able to compare it to NP and SAT and all of that, but just at the within the computational resources space, I mean, it's it's the policy horizon, the time horizon depth times how many policies you have times how much time times how many hidden states there are. It's just like how many things do you have to keep track of broadly, and then branching time active inference is using heuristics to significantly reduce that complexity. But they presented several complexity calculations in this paper, and with empirical runtimes. Yeah, Ali.
Yeah, so in branching time active inference, the attempt was to reduce the complexity class of the problems from exponential complexity to linear complexity. So that was one way to do it, but a much more recent one, actually, it was from a few days ago, is this recent paper by Friston et al., namely supervised structure learning, in which they have proposed an alternative way to reduce the constrained mutual information of expected free energy. So it's again another way to reduce the complexity class of the active inference, or probably any other inference-based problems as well. So yeah, there are some attempts which they explicitly address the problem of complexity of real world active inference problems. But one of the main criticisms of, or at least one of the main drawbacks of implementing active inference models in past years was exactly based on the exponential complexity of higher level generative models and the ensuing, intractability of the computation that resulted from that.
Yeah.
Yes. So yeah, so when I look at the generative model and the optimization problem, it seems to me that it suffers the same curse of dimensionality as we had in dynamic programming. So basically your time exponentially increase in the number of states. the more number of states, whether it's hidden states or explicit states, and also the number of policies. So if, I wonder what kind of a trick they have been able to use to reduce the computational complexity from exponential to a kind of polynomial or linear. Linear is a form of polynomial, right? So exponential is much faster. Sorry, exponential is much slower than linear. I mean, linear in terms of input, so our input are in the active inference model minimization problem, the model needs to use data, which are the observations, the dimensions of states, the amount of policies. Yeah, there's one issue. I wonder if someone can help me. So the active inference defines the policy as the action they take at each time point.
Affordance is the action. Affordance is the action you take at each time point. Policy is a sequence of actions for a given time horizon.
Right. So it's a sequence of action at each time point. So my understanding of policy is that they are actually they are not only a function of time, not they are a sequence of time, but also they are a sequence of states. Depends on what states you're in, you take different actions, not just the time, but also the hidden states. So I wonder if they are the same.
If what are the same?
So action as a sequence of time versus action as a sequence of states and time,
Like ideally, whether you take the action at 2 p.m. or 7 p.m. or 11 p.m., like the number of the time policy selection should be invariant unless the time is the determinant factor for which policy to take. So the time number itself shouldn't matter. And then as to whether a given observation or hidden state has a bearing on policy selection, that's the question. There's no reason to address that question in the abstract, because obviously we can imagine situations that do and don't have that. And also, while we're in this space of computational accelerations, like in the most recent message passing live stream, now there's direct policy inference without expected free energy. So, I mean, that's why we just hold on to our hats and stay in the game, because it may not be required to iterate over all policies with an expected free energy, compare the expected free energies, do tree search on EFE. If you read the paper 56 and watch the discussions with Magnus, we heavily discuss this direct policy inference technique. So sometimes the kind of all by all is like the pedagogical or just the first sketch. But don't wait on the sideline because you're worried about a computational slowdown that may or may not happen. Either jump in and find out about that slowdown, or jump in and then you'll find out that there's no slowdown, or that by the time that you get to actually building that model in 3 months or 6 months, that the computational environment has evolved. But the generalized,
So I'm supervising my student to build the active inference model, and when so you have to define the policies,
not
what
really.
it is.
You define the
state.
You define the affordances, and then the time horizon.
What is the affordance?
Those are the actions that can be taken in a moment. up, down, left, right, 4 affordances. And then we're going to do, 2 time steps. And then there's 16 policies. The policies are just the enumeration of all the possible sequences of affordances of that length. So policy construction is trivial. Policy evaluation traditionally has been done with the EFE. But now there's an even more direct way to do it. It doesn't mean that this is the best way to do it in every single person's situation for every single problem. Just that there is a technique now where you don't need to do expected free energy based comparison. You can do generalized free energy based direct policy inference. It just is that way.
Yeah, so I'm repeating myself. Sorry, just one last time. Hope somebody can help me. So policy is defined as function of time, right? So in the sense that you see it's a sequence of action. That's the policy defined in the textbook. The sequence of action, at time 1, what you do, at time 2, what you do, left or right, those actions. But in general, in my area, in my dynamic programming area, the policies are defined as a function of state, not only time, but also state. In our example, for example, whether it depends on whether you're hungry or not hungry. If one of the state of your senses data is that whether you're hungry or not, then your policies, it actually depends on whether you're going to go for food or just take a bite of some food. Depends on your state, the hungry or not hungry state. Not necessarily depends on time.
Well, yes, in different areas of control, terms like policy are used slightly differently, but broadly, we're talking about the same thing, which is a policy is a sequence of actions, and you can construct the model to be borne upon by hunger or not. So whether or not a given observation or hidden state has a bearing on a given policy selection, that's up to the modeler. That's not going to be addressed by active inference textbook group generalities. But yeah, if you make a model where hunger bears upon the choice to eat an apple, then you have your answer. If you do it where it doesn't, you also have your answer.
Okay.
But there isn't an in principle answer to a situational design.
Mm-hmm. So what you're saying is that as a researcher, I can define the policy in different way, not just the sequence of action over time, but a sequence of action over states, over hidden states, for example.
As part of constructing the entire generative model, so A, B, C, D, E, and so on, you're right. You decide not just the affordances and the time horizon, which define the policy space, but you also establish the sparsity and the connections of what else is included. So if it's just a thermometer, and then the thermometer is unrelated to, a slot machine player, that's what you have. But if the slot machine's conditioned on temperature, that's what you have. If the slot machine's conditioned upon a taste sensor, that's what you have. So it's like a toolbox for us to take those steps and ask what if. But we can't return to the framework and ask about whether certain factors influence each other or not. Again, because we can just quickly think about examples where they wouldn't. That's what chapter 6 is about, is defining the whole generative model. We don't just hard code the policies.
Yeah, thanks. I need to think a little bit more how to generalize the policy, to extend the model in chapter 6 to more general policy definition. Okay, thank you anyway for clarification.
Yeah, oh yes. Let's look at a few of the questions. This is a great starting one. Section 10.4. There's a song lyric. And then this person has written another verse from that song that's a little bit less juvenile violence in theme. Okay. Anyone want to? Yeah, go ahead.
Yeah, I just wanted to, I need some clarification, and I think I don't know if it's relevant to Wanshan's question. But there are states, hidden states, that we attempt to infer from our models. That's my understanding. Then there's perception, and then there's action. And one of the things that the themes in the book is that action and perception, if I understood this correctly, are seen as one and the same thing. Could you elaborate on that?
A lot of great questions. You said that through modeling, like we find or we discover hidden states. A slightly more,
because we can't view them, we can't see them, so
right.
we have to infer them.
Right. We have a microcosm of the ActInf agent, which is that the ActInf agent is only getting its sensorium, the inbound, and its actions on the outbound, and it is proposing latent, unobserved, or hidden causes of sensory phenomena to bound its surprise. So in this kind, when we write this kind of a model, like figure 4.3, we put the hidden state down, temperature in the room, we put the observation down, thermometer, and then the agent does the inference on the hidden state. So, but we constructed the hidden state space to be fixed. Or structure learning is like when the agent is going to be like rearranging combinations of hidden states and learning the structure of the world for itself. Action and perception are part of a unified, unity is plural at minimum two. Perception is not action simply. Now, if you look across a blanket, one agent's action becomes the other's perception. So in that sense, action and perception are just kind of like, whose perspective are you taking from the blanket? Like, screaming into the environment is the action from the yeller, but then it's the perception from the environment. So that's one sense, but action and perception are unified in active inference, not by eradicating their differences, but by understanding their complete articulation, which is the two directions of traffic across the blanket. So it's not that, listening is the same as kicking your leg. It's not that perception is action. It's that they're part of a unified cognitive framework that has a unified imperative with free energy minimization, unified handling of variables like this, and so on.
Okay, so having said that, having said that, for one individual agent, that when we move into really complex systems, like the social insects you work on, for a complicated system like an ant's nest, the system is the ant's nest. Can you tell me, just in plain English, what's this? What are the actions, examples of actions, and examples of perceptions in that system?
Sure. Well, although the ant colony system is like the evolutionary replicator or the Kantian organism, in the active inference model, we made an agent-based model with a nestmate. And we used exactly the figure 4.3 type generative model.
Right.
Perception was pheromone and action was movement. So broadly, the selection of the perception and action of the agent is similar to any other agent-based modeling technique. If you modeled the ant colony as a single organism, that's a totally cool and valid model. There's always a plurality of models available. So modeling a single colony as the agent, maybe if you wanted to model like a field site with just several thousand colonies and you didn't want to go into the nestimate level of detail, or maybe the nestimate level is too coarse-grained and maybe you need to do an organ-specific model. These are maps, not territories. So it's whatever you need to do to take the next step on your path. Not about there only being like one ants model.
Right. So then so as systems, so systems to me are just, I can't think of any system that, at least in the phenomena that I'm familiar with, where there's anything, an individual unit. Because even if we go down to a cell is a system, you know, or if we go down to a microbe, the microbe is a system, and they're very complex systems. So it just seems to me that there are systems and nested systems within systems and interacting systems, and all kinds of systems interacting with each other, etc. So, I know there are different ways of thinking about complexity. I think about it right now in a very qualitative way, but it seems to me that, like, for example, in the ants nest, you have all kinds of systems going. You have the system of the, you know, maybe the queen and everything that's associated with her reproduction. Then there are the systems of all the workers keeping the brood clean and so on and so forth. So there are so many ways that you can take these concepts and identify Markov blankets that are relevant to different agents within systems, and that can be then blown up to a whole system. Am I understanding this correctly?
Yeah. Yeah. I mean, at the most zoomed out, that's also true of linear modeling. You could say, well, we could do a linear regression of the queen's femur versus the number of seeds per minute per day squared. You know, there's no limit to the amount of linear regressions, fMRI analysis. So there's just science and instrumentalism as a technique. There's never any ending to how many models can be. This is not ActInf specific. Now, you said there's nested interacting blankets or nested and interacting agents. Also, very true. We have enclosures of systems and laterally interacting collective behavior, but those are expressions about the territory. You're talking about how the colony really is. You could choose to model it in different ways, and active inference gives us a qualified way to stop that infinite regress by saying, yeah, there are organs within the nestmate. They do have a midgut and a brain and all this. We're modeling this level. And then that's the perfect stopping point for then a future study to pick up there and go one level deeper into the blanket. So it's not that one study must make all possible models and maps of all detail. It's actually leading to a more principled way of collaborating across these different systems. That's the goal of the infer ants and analogously for other systems. I mean, why do we have so many square one models of ant foraging, but there's never like sustained development of multiple labs with multiple species looking at different foraging environments? Because it's easy to make that custom model of that one ant in that one setting. But then to generalize it to multiple ant species or multiple settings, let alone tasks other than foraging, it's very challenging. So then the literature is basically littered with kind of toy models or intuition pumps, but there's never a strong substrate to build a real extensible model like a Linux kernel for agent-based simulations. And those have been tried, but then those systems that try to generalize agent-based simulations themselves get mired down in technical details and frictions of accessibility. But you've definitely identified the key aspects of what we can explore. And that's why chapter 6 is provided. Chapter 6 doesn't say, here's how nature is organized. Chapter 6 says, here's how you build that generative model. And then how does chapter 10 end? Build the model and get surprised. It doesn't end with, great, now you've established how nature is.
Got it. So my next, I go with my stupid question. My next stupid question, but I have to ask it.
Yeah.
Because it seems like throughout the book, there's like this, in some places it's very clear, and I've seen it in other contexts where it's stated clearly that what the goal is to take this understanding, this deep structure based on the concepts and the architecture of the ecosystem of active inference, whatever it looks like, you know, for whomever, but there's kind of a consensus around certain ideas that hold this conceptual framework together. But the idea is that to be able to take that and then go into artificial intelligence and machine learning and say, this stuff that we see in living organisms, this deep structure, we can translate it into a completely artificial system and recreate actions by translating this deep structure into something that works in a machine. And then if that's the case, then I guess for me as a social scientist is the deep inference here that there is really no boundary between living and non-living systems from an active inference perspective.
There's a lot to say on that. One could debate whether the construction of a synthetic anything, synthetic chemistry, synthetic drawing, a synthetic active inference agent, does constructing a synthetic anything legitimate any claim about the territory? Just making an arts and crafts project doesn't change the nature of the trees and the sunset. So that's one point. Second point would be, yeah, instrumentally, if not further, we have a strong continuity of diverse systems, inert systems, sleeping systems, active systems, and so on. So from an instrumental descriptive perspective, we have an integrated modeling approach across different kinds of systems. Again, this doesn't mean life and non-life are the same.
Exactly.
It means that there's a palette for people to say, this is what I mean by life. And I made models that are on either side of the line, and this one's in the gray zone. And someone can say, well, my line's over here. Well, that's just the fact of the matter then, that those people have those different lines.
Yes. Okay. Thank you. Appreciate it.
Yeah, these are, let's see if we can look at just so that we can. Okay, I'll start on the bottom.
Mm-hmm.
Okay. Yes, thank you for this one addressed earlier. Yes, everyone is encouraged to join our broader educational efforts and to enrich the textbook group where we actually will do these things. Which sections discuss, is Bayesian computation the most effective problem-solving system for minimizing free energy? Not sure if in the book per se, they might discuss Bayesian optimality Other people I know elsewhere take more like kind of first principles. Here's why things should be or ought to be Bayesian. But suffice to say, the framework doesn't rest upon Bayesian computation being the most effective. This is just a framework that we can use to describe any system. Now, what's the most effective to actually do it? That may or may not be doing Bayesian statistics. But the analytical formalism will never fail us as observers. But that doesn't mean it's the best way to build it from the inside. It'd be helpful to provide definitions for thermodynamics, free energy, and of ActInf variational free energy. Throughout the book, free energy is used interchangeably with variational free energy. In this book, they are probably unless explicitly mentioned, they're only talking about variational free energy. They're never talking about Gibbs unless they specifically called it out, and I don't think they do. They're only concerned with informational free energy, not thermo. Sections on the term of free energy. Yeah, definitely. There's always ways to connect it back. And let's go to the strongest. Alex Kiefer. Psychophysical identity and free energy. Livestream 22. This is the strongest statement, or one of the strongest statements made, that the thermodynamic free energy of a system directly encodes variational free energy. So we're walking that pedagogical line. You know, they're different concepts. You could link them how you want. And then Kiefer just runs in and says, no, they're the same. Or there are systems for which the thermodynamic free energy flows do entail variational free energy flows. Okay, definition of brain. Definitions for mind, brain, and behavior. Yeah, I mean, there's the author's definition, and then there's our ontology. And we meet every week to update the definitions and to translate them and to use them more coherently. So if people especially are interested in definitional questions, let's do it. Brains and centralized nervous systems. Not exactly sure what you mean by the brain is a recent development. I mean, they're going back to the last common ancestor of vertebrates and invertebrates. There was a centralized nervous system, and it changed in structure and function, even in the last tens of thousands of years.
In that question, it's kind of along the same lines of the what's living and what isn't. In this, so I guess, you know, you're right. I mean, it's about you as the observer and researcher to decide where you know, how you're going to define things, what your affordances are, what is the system that you're working with. But when I was first reading through the book, I was just thinking, is this only referring to systems where you have to have a nervous system? And then what I was talking about is that the human brain in terms of the neurological variation that's out there in nature, it just has, very different structure, very complex structures. Anyway, so it's along the line. So, do you have to have this neurological kind of sensorium in order to use active inference? models, and I think you've answered that question for me. That no.
Good question. It absolutely does not require centralized nervous system or nervous cells. It could be a pendulum. It could be an inert rock on the ground. It doesn't need to be any kind of biological life form or any kind of anatomy.
Thank you.
Yeah.
That's really great.
But
Here.
again, but most of the work has
Mhm.
arisen from Karl, Friston, and colleagues doing human neuroimaging. Again, every single time in chapter 5, that's what we emphasize. Chapter 4, generative model. In essence, chapter 5, they go to the case and the setting where the most work empirically has been done, which is human neuroscience. But there's so many other ways to go.
Thank you.
Okay. Is this a question or what about this?
Can't really see, it's too small.
Opportunity to expand on niche construction. I agree with
Yeah.
this.
Oh, yeah.
Okay. Yeah, I mean as everybody, that sequencing question we talked about earlier, like the textbook is just one sequence. And so some people are going to say, connect it more to what has empirically been done. And I want to understand how brains work. I want to have that first person driver's seat perspective. I want the stories to be about me picking up the water, me getting out of the chair, me listening to music. Other people are going to say, isn't it about bigger than humans or different than humans? Shouldn't we use only the technical mathematical? Aren't appeals to personal experience possibly even misleading? Everyone's right. That's why we need a bigger knowledge system that can generate those sequenced paths. So if people want the human 101, no math in this language, they can have that path. And if somebody wants a different language, different technical level, no human examples, that is also going to be fully consistent.
And so so Chris Field's course on information physics as information processing, is that in this context, trying to connect dots here, is that a way of saying, or his perspective is, we don't have to make the work so complicated. At the from a quantum physics perspective, we can actually think about active inference in a different way. And trying to get at the deeper structure of information processing.
Yeah, this textbook was written probably largely between 2018 and 2022, maybe even 2021, because it was published in March 2022. And it was centered around Friston's 2019 particular physics monograph, developed a lot. The quantum free energy principle work with Fields, Glazebrook, Levin, Marciano et al. Only was in 2022, livestream 40. So this textbook does not include any quantum informatics. Chris Fields and colleagues with their backgrounds in the quantum information sciences made that connection between free energy principle and quantum. So that connection is basically unaddressed in this textbook. Only in the most minimal possible way, hinting at the Bayesian mechanics. So this textbook is, those who love the history and philosophy of science, again, let us reconvene to write these histories. But this book is in some ways like a coda on the 2010s of active inference. because already in the 2020s, we're heading off in some new directions. And so it's kind of like an inflection point that consolidated a huge amount of the past work. But now with message passing and Julia on this side and quantum FEP on that side and far more empirical applications happening all around, it's a different environment for doing active inference learning and application, and for writing a textbook, as we could ask Sanjeev about. So this textbook's not everything. And again, just from a chapter 10 perspective, in only about 200 pages, 200 very short pages, what they've done is incredible. And that's why we can always return to it. And yeah, even though it's only been 18 months since it's being released. But this is the discussion we've had. That does not conclude cohort 4. I hope that people return next week to discuss more, and yeah, update things, develop things, add projects, add questions, develop the answers. Thank you, everybody.
So thank you. Appreciate it.
See you next time.
See you next time.
Thank you, Daniel. Bye-bye.
Bye-bye.